So we will wait few more minutes and after that we will start today's class. So we will start today's session. So first of all, I would like to welcome you to this live interacting session. This is our 11th live interacting session. And I am Niloy, a PhD scholar from IIT Bhubaneswar. I am your TA for this course. And the instructor of this course is Professor Subhashish Datta from IIT Guwahati. I hope that all of you have gone through these courses which has been taught by Professor Subhashish. So in the live in this upcoming live interacting session, we will discuss about some concept of fluid mechanics. In the previous classes we have discussed about this Navier-Stokes equation and all this. But what I would like to tell you is that please go through the topic that has been taught till the week 10. So the basic concept will help you to go through this upcoming concept, and even your examining is upcoming. So that will definitely help you to refine your strength and knowledge. So before starting these courses, I want to give a brief description about this course. So this fluid mechanics is an interdisciplinary course for the engineering student, mainly this mechanical, chemical and civil engineering. So in these courses, we will be dealing how to solve real life problem, like if you are designing an aircraft, or if you are designing a dam, and any such types of problem, you need this basic and the fundamental concept of fluid mechanics and how the fluid flows, types of flow pattern, and all these things is quite essential for you. Even for the visualization purpose, you need to know this fundamental. So in the last week we discussed about this Navier-Stokes, which is quite essential in the point of view of fluid mechanics. And before this, we have discussed about this mass conservation equation continuity, which is the continuity equation, and even Bernoulli's equation we have discussed. And all these basically are linked with each other, and how you will apply this in real life problem. That thing we have discussed earlier. So in these courses, what we will discuss about, we will basically discuss about how to solve this Navier-Stokes equation. Mainly, we will deal with this boundary layer approximation, which is quite essential concept. So as I will assume that you have gone through these courses, so my approach will be like I will be providing you a question and I will give you a few minutes time to solve. And if you are not able, if you and I will give you few minutes time to solve, and let's see how you have gone through these courses and this topic. And after that, I will discuss this question with depth, concept, and all these things. So that will be my concept. So since it's the boundary layer approximation, so let me discuss about this boundary layer initially, right? So to discuss this boundary layer, what I want, so let me draw this for you. Just a minute. So I think the sound is audible. Hmm. So say it's a surface, okay? So any surface, maybe it's I consider this as a surface at rest, okay? So if this is a surface and fluid is flowing over it, so this fluid is flowing over it, okay? So like this fluid is flowing over it. So a fluid particle, so I take another color for you. So this is a fluid particle which is in touch with this surface. So at these cases its velocity is zero. So and as you move above this and a point just above it, it has certain velocity which is greater than zero. And as you move further, its velocity is much more. Like that way, its velocity will increase, and until this layer, this is the free stream velocity. If it is the u max, so that means that from 0 to u max, it is steadily increasing, right? So because of the change in this velocity, a region is forming. This region is known as boundary layer. Okay. So, because of this, a boundary layer is forming. So, like this. Okay, why this boundary layer is forming? Because the fluid particle that is in touch with this surface have a zero velocity, and the particle next to it that is just above you has a velocity slightly more than this, and this will goes on increasing until and unless the velocity reaches this free stream velocity. That's why it is known as this thin region is known as boundary layer. Okay, so let me define this boundary layer in a quite easier concept. So, I am giving you few more concept on this. As I have said that this is our boundary layer, right? Say this is outside this plate. So inside a pipe we are flowing, not a pipe. So it's a velocity we are just providing. Say the velocity of air initially, but once it comes in contact with this surface, maybe it happen that it have zero slip condition, that is the velocity of the particle near this surface should be zero, right? That thing can happen. So when this fluid is flowing over the solid surface, let it take as a point P anywhere, say here or here, anywhere a point P, which is the pressure, static pressure at that point. Okay, and say this x is the distance of the point from the starting region. Okay, so I can write here initially I don't know what is the pressure, and so del P means change in pressure from this point to this one, let us assume, and this change in pressure with respect to change in the distance, that is pressure gradient. So this term is known as pressure gradient. So that indicates the change in pressure in the horizontal direction. Okay. So if it is a flat plate, thin, and it is a smooth thin plate, it's a fully flat plate. Okay. So and the velocity is parallel to it. So what will happen in that case is the pressure gradient is zero. That is no change in pressure you will observe when for flow parallel to free stream. Okay, over a smooth thin plate. Okay, that is the concept. So if the that means the pressure gradient is zero. So in certain cases, if the pressure gradient is zero, that implies this boundary layer thickness increases continuously. Say with respect to in the x direction, no change in pressure. So in that cases, you will see this boundary layer is going on increasing as you move further along this x direction. Okay, that is for a flat surface, right? Now I will be talking about a curved surface. Any confusion up to this? So that is for a flat surface. Now I will be talking what will happen in a curved surface. So in a curved surface there is always pressure gradient. Pressure gradient, there is certain pressure gradient. Like say this is a curved surface. Just a minute. Say this is a curved surface. So I am taking few point A, this is B, this is C, this is D, and this is E. Okay. So these are few. Assume this surface is fixed, or that is the surface is not moving. It's a stationary surface. So certain fluid is flowing over it. So I am just flowing some air. There is certain velocity there. Okay. So you see, from the point of view, you just observe, see one thing. If the fluid is flowing like that way, so there is certain point where the pressure gradient will not be same, because the flow will not in direct contact with the surface as it's a curved surface, right? So that's why in the region ABC, assume this region ABC. So what happens? This flow area decreases. So whatever be the in case of steady flow, In case of a flow over a flat surface, the whole surface is exposed to the flow, but in case of a curved surface, this whole surface is not exposed, right? So what will happen? Happen that this velocity will slightly increase. Okay, this means this flow is accelerated once it is coming in contact with this curved surface. Because of this curved nature, its velocity increases. Velocity increases means just means A, B, C. What will happen? This velocity increase. Velocity increase means acceleration will increase. The flow is accelerated. So what will happen? This pressure gradient from A to C. So if I draw this pressure gradient, this is A, B, and C. See, if the velocity is increasing, the pressure will definitely decrease. So this line, so I'm representing a green line, you will see the pressure will decrease here. So if in this point, if the pressure is PA, and in this point, if the pressure is PB, which one will be greater? PA will be greater. So up to this I can write d of P by d of x, that should be less than 0. So as the pressure is decreasing, so this pressure gradient is negative. So in this curvature, what will happen if this curvature is like that way? Initially the pressure gradient is 0 because of this curvature nature. Here this velocity will increases and the acceleration in term will increase. Okay. So this pressure gradient is, so if I talk about this velocity uh, boundary layer, the boundary layer is initially like this here. Okay. And the velocity profile, you know that in contact with the surface the velocity is almost 0, but as you move as you go further, the velocity of the velocity profile increases. So this is the velocity profile here. Similarly here, this is the velocity profile. Okay. So what will happen here, this velocity sudden increase in velocity is there, but as you move, this profile is a little bit steeper. Okay. So this is up to point C I am talking about. So in what will happen in this after this point C, or in this point C. So again in this point C, this pressure gradient will be 0 because it is at the top point. So here this velocity can easily target the surface. Okay. For say if the, and again after this after CDE, in this point, if I talk about this point CDE, what will happen in this point? The as the pressure is getting minimum at C, already this pressure is minimum at C, right? So along this path CDE, the area of the flow increases and the velocity will increase because it's a low pressure, and as it is moving there, where the here also this pressure will be more definitely. So this velocity decreases here. So as this here, so what will happen in this region? The velocity decreases, which implies this acceleration is also decreasing, right? Therefore, this pressure gradient, as the velocity is decreasing, that means pressure will increase. So this point D and E, you will find this pressure gradient will increase. Okay. So as the pressure gradient is increased, so initially in the previous we have discussed that if the pressure gradient is zero, that implies this the boundary layer thickness will increase. So here as the pressure gradient is less than 0 in ABC, so this boundary layer will be there. But as this pressure is greater than pressure gradient is greater than 0, what will happen? So though the boundary layer is generating up to a certain after a certain limit, what will happen? Here a backflow is generating. So like this types of flow will generate. That means the boundary layer that you will be observe is up to this region, and below this there is a reverse flow. Okay, so if I draw the velocity profile up to this point, so it will looks like the previous one, but in these cases if I draw this velocity profile, what will happen? It is somehow like this. That means here the flow is in the opposite direction, and in the boundary layer the flow is like the previous one. So that is basically the difference. So if the pressure gradient is greater than 0, what we will observe? This velocity profile is quite changing. So in this portion of disturbances, the velocity is in the opposite direction, right? So as you observed here, and in the boundary layer region, this is same as that one. So this region is called separation, boundary layer separation. Here this point is called boundary layer separation. So up to this it is clear. So this is the fundamental concept regarding this. So I hope that you understand this thing. So now I am moving to a question. So based on this concept, and I hope that you will be able to answer this one. So this is my first question for today. So which of the following is responsible for the separation of this boundary layer? The first is the negative pressure gradient. Negative pressure gradients means that dp by dx, dp dx less than 0, and positive means greater than 0. Low viscosity of fluid and none of the above. So please try to answer this question. I am giving you 1 minute time for this one. So Vidisha has answered option B. Yes, it's the correct answer. This is the correct answer. So already I have explained this thing. Just the thing is that if the pressure, always remember one thing, negative pressure gradient means pressure, if someone talk about this negative, in any cases, pressure gradient, irrespective of the type of boundary, whether it's a curve or any type of boundary, irregular boundary. So this pressure is decreasing implies pressure decreases along flow. Okay. So if the pressure is decreasing along flow, that means initially there is high pressure. and after it is moving to low pressure. So which is usually the case. So in that cases, the a fluid that is flowing, it has high tendency to remain attached with the surface. Okay. And in the positive, if I talk about this positive pressure gradient, so this implies P increases along flow, pressure increases along flow. So that means low pressure, the flow is from the low pressure to high pressure, right? So which indicate what this indicate that the velocity is decreasing, right? So the particle is moving along the surface in quite slowly. Here as it is moving from high pressure to low pressure, so the velocity will be more, V is more. But here as it is from low to high, so V will be less, velocity will be less. So this fluid particle that is moving along the surface, it is moving quite slowly compared to normal stream velocity, right? So that means they will losses a particle is losing energy. So initially if it is moving with u velocity and if it is losing some velocity, that means it is losing some kinetic energy. So even in some time the energy is quite less, so that the backward flow can be generated, and because of this backward flow this boundary layer separation happens. That's why this positive pressure gradient is the correct answer. Okay, so that's why. And any confusion up to this, please tell if you have any confusion regarding this, because once you will be able to answer these types of question, majority of the question is based on the same concept. That's why I am asking you this thing. So, okay, I am moving to this next one then. And here another important question. So, low viscosity of the whether low viscosity of the fluid can be the answer. So, this viscosity is, just remember one thing: viscosity determines the thickness of the boundary layer, but it doesn't causes the separation of the boundary layer. Remember one thing: this viscosity is the factor that will determine whether this boundary layer is will be more or will be less. So that is the thing. So option B is the correct answer. So it's a numerical question. So here it is given. Hmm. So this condition is given to boundary layer thickness is given as, and also the distance is given. So you are asked to find the ratio. You are asked to find delta 1 is to delta 2. So I hope that maybe you haven't know this formula of this boundary layer thickness, right? Yes or no? Please inform me. Okay, I'm giving you this formula. So basically this formula is delta is 5x by root Rex, which is for laminar flow. Okay. For turbulent flow, it is basically 0.38x by Reynolds number to the power 1 by 5. That is for turbulent flow. So that is basically this formula. So remember one thing. So in any question, irrespective in this question, whether it is given whether it's a laminar flow or turbulent flow, any information is given or not, just tell me one thing. So no information is given, like whether it's a laminar flow or turbulent flow. But see, it is talking about in general cases from leading of flat plate. So we have talked about this flat plate. Basically, in case of this flat plate, we assume it to be laminar. Okay. So considering it as a laminar flow, you just try to solve this one. I am giving you 1 minute time, and after that I will discuss this concept with you. Okay, I am solving this one for you. I hope that you have answered option D. Okay, good attempt. What about Ridvi? No response. Okay, let us see. So Vidisha, your attempt is quite good, but the what mistake you have made? Let us see. So see, this formula, as I have said, they consider this laminar flow. So what is the Reynolds number? You know the formula of Reynolds number. Reynolds number is inertial force by viscous force, and you also know this formula, right? So all that means even if I write it in terms of kinematic viscosity, what I will get, this is ux by, hmm, I can write, okay. So that means here I can write this is proportional to x, assuming that it's a this talking about a same plate. So in this plate, this free stream velocity would be same for this. Say it is a free plate, it is a plate. So if this is the free stream velocity, so this free stream velocity will be same for throughout this plate. So that's why this u even the viscosity will be same because the we can consider this condition, atmospheric condition and all this same. So this kinematic viscosity will be same. So Reynolds number is proportional to x, right? So if the Reynolds number is proportional to x, I can write in this formula this is proportional to the denominator is x and the numerator this can be written as root x. So which means it should be root x, right? So now I can write as I have got this is proportional to root x. So I can write this 1 by this 2, this equal to this 1 by this 2. So what is x1 is given as 1 and this one is given as root 4. So that is 1 by 2 which is 0.5. So the correct option is here 0.5. So I hope that you understand your mistake. Okay, then I am moving to this next question. So just remember this thing, these two formula is quite essential. Okay, then I am moving to this next question. So this is another theoretical question. So in this question it is asked the boundary layer approximation of this Navier-Stokes equation is most accurate when. So this is the question. So this condition is that the flow is highly turbulent, the Reynolds number is very low, and the Reynolds number third option is Reynolds number is very high. The velocity gradient is uniform across the flow field. So please try to answer this one. I'm giving you 1 minute time for this one. So I'm just giving you an hint. Use this concept of Reynolds number. So Reynolds number basically is inertial force by viscous force. So just try to understand what will happen if the Reynolds number is low, if the Reynolds number is high, or the flow is highly turbulent. So try to correlate this Reynolds number concept with this one, and you will be able to answer this, I hope. So please try. I am giving you 1 minute. Any idea? So can I? So so Ridvi is saying this is option B. Okay, let us see whether it's correct or not. So just see this directing session or this course, this concept of boundary layer approximation is quite essential for you because even if you will gone for any interview, they will ask question about this. So the question is this: is boundary layer approximation of the Navier-Stokes equation is most accurate? So for this boundary layer approximation of this Navier-Stokes equation, so basically they are assuming some point. So what are those points? The first point is this: the boundary layer is very thin. I represent this boundary layer as B dot L is very thin compared to the overall dimension of the body. So basically, if this is a body, the boundary layer should be small. Say if the boundary layer is this much more, then this Navier-Stokes equation doesn't hold good. So this is first thing. So for this boundary layer should be thin. Okay. Next is that within this boundary layer, say this is the boundary layer, right? So this in this direction, this is in the x direction and this is y direction, right? So next point is that within this boundary condition, within this boundary layer, the velocity gradient, that means say this velocity gradient deu dy. This is in the y direction. This velocity gradient should be much more higher than this x direction. That means we can consider this as in the x direction, this velocity gradient should be considered as negligible. Okay. The third point is this pressure gradient should be negligible. So in any point, if you found out, say in the first slide, what I have said dp by dx should be equal to or less than 0. If it is greater than 0, then the boundary separation will be happen. So this pressure gradient should be negligible. That means it should be also negligible. So what is negligible? The pressure and the velocity gradient along this axis should be negligible. But say this is the boundary layer. Outside this boundary layer, whatever may be the pressure and whatever may be the pressure inside this boundary layer, there should be quite different. So there will definitely be pressure variation. But in the inside this boundary layer, the pressure variation should be negligible. So that is the main point. Okay, so now if I talk about this flow is highly turbulent. So this formula, this boundary layer concept is for both laminar and turbulent. So this first point cannot be exactly correct. Okay, so this Reynolds number is quite low. So if the Reynolds number is low, what that indicates? So Reynolds number means what I have said. This means inertia by viscous. So if Reynolds number is low, so I can say that this viscous term is quite more. Okay. So in that cases, what will happen? So if the viscosity is more, so what will happen? This, as I have in the previous one, I have said if the viscosity, more will be the boundary layer. So as the Reynolds number is less, as the Reynolds number is less, implies viscosity is more. What this implies? This implies boundary layer is better, is thick. So, but in the assumptions of this Navier-Stokes equation, we have considered this boundary layer very thin. So that approximation is wrong. Next is this temperature Reynolds number is very high. So if I talk about this high Reynolds number means here inertia should be more. If the Reynolds number is more, that implies this inertia force should be more, right? So this as the inertia force dominant this viscous force, so that means we can also inversely we can also say that this viscous term will be less. So as this viscous term will be less, this implies this boundary layer thickness should be less, that it should be thin. That means it holds with our first assumption of this Navier-Stokes equation. So option C is the correct answer. And coming to this velocity gradient uniform across the flow field, that is not correct, because what I have said that in the y direction this velocity gradient is quite high compared to that in the x direction. So that's why this is also not correct. So whether you understand this concept, please let me know. So any confusion regarding this? So why Reynolds number is very low, it doesn't hold good for this question. Is it clear? So basically you need to remember these three assumptions, or the first assumption is that this boundary layer should be thin. If you have to solve this Navier-Stokes equation using this boundary layer approximation, you have to remember this the boundary layer thickness should be thin, and the next is that the inside the boundary layer the velocity gradient in the normal direction or the y direction should be much more greater than that in the x direction. The third is that there is negligible pressure gradient in the boundary, in this boundary, inside this boundary layer. Okay, outside there can be much more pressure, so that is not our point of dealing. So that's why this correct answer is option C. The Reynolds number is very high. Okay, so I hope that you understand this. So I am moving to this next question. Again, this is a similar types of question. So here you five options are given. You have to check which one will be the correct. I am giving you 2 minutes time to analyze and answer this question. Anyone? So please try to answer. So no need to worry. Maybe it will be wrong, but at least try to attempt, because that will help you to test your fundamental. So I am going to solve this one for you. So I have received one answer. Anyone else? Okay, I am solving this one for you. So see, a few minutes, if in two question back, I have given you this formula of this thermal boundary layer thickness. For laminar flow, it should be like this one, and for turbulent flow, it should be 0.38 x into Reynolds number to the power 1 by 5, right? So see, if the Reynolds number is high, in that case, forgot about this thing. If I talk about only about this thing, you can take this one also, but for your understanding, I am taking this first one. If the Reynolds number is high, so that means indicate this one should be less. Also, this thing you can understand using this concept of Reynolds number, which is inertial force by viscous force. If the Reynolds number is high, that means inertial force will be more and the viscous force will be less. So which indicate that as the viscous force is less, the boundary layer thickness will be thin. So option 1 can be correct. The boundary layer approximation may be appropriate for free shear layer. Yes, it is also correct because if you talk about this jet, you have seen jet. In this jet, this boundary layer approximation also holds good. Okay, so this one is free shear layer means for this jet flow, or you can go wake flow. Next is this boundary layer equation or approximation of the Navier-Stokes equation. Yes, I have explained it in the earlier question with some assumptions. So that is also partially correct. So the fourth is this boundary layer approximation bridges the gap between the Euler's equation and this Navier-Stokes equation. So see, in this Euler's equation, which is basically this Navier-Stokes equation, where they neglect this viscous term. Okay, and the Navier-Stokes equation consider viscous term. And in case of this boundary layer approximation, it consider viscous term only when it is necessary. Consider when mainly near the wall. So it basically considered this near the wall. That means if we have to talk about this boundary layer approximation, what will happen? See, if there is a question, you need to find out certain solution of this question. There is a flow. So only this boundary layer is near this surface. So if you solve this boundary layer using this boundary layer approximation, you will get the solution for this region, and whatever may be the solution you get from this region, you can use it for this Euler's equation without using this viscosity. That will not affect your answer that much. Okay, so that's why this option is also correct. So that means all these four options is correct. So option A is the correct answer. All the above should be the correct answer. I hope that you understand this. Okay. So I am moving to this next question. Please try to answer this question. This is another such types of question. Just now I have explained about this thing. I hope that all of you will be able to answer this one. If you have any confusion or you are not able to understanding this concept, please let me know through this chat box. I will explain it again for you. So anyone? Yes. So Pragya and Riddhi, both of you have answered option B. So let us see. Yes, it's the correct answer. So because as already I have discussed that if there is no viscosity, what equation we can use? No viscosity or we can use Euler's equation. But if there is viscosity, we can use Navier-Stokes equation or boundary layer approximation near the wall. So that's why this boundary layer approximation, for this boundary always there should be viscosity. So in viscid region means no viscosity should be there. So this is not the reason why this boundary layer approximation is required. You can directly solve it using this Euler's equation. So option B is the correct answer. Good. And as I have talked in the jet also in the previous slide, jet and OAK, in this region in one direction there is boundary layer formation. So that thing is also accurate here. And thin region near the solid world, that is the fundamental of this boundary layer approximation method. So that's why all these three A, C, and D are not the correct answer. So I'm moving to this next question. So in this question, for flow along a flat surface with x being the distance from the leading edge, the boundary layer thickness grows like. So that is another fundamental question, and I hope that you will be able to answer this one because I have already shown this derivation in the first slide, probably. So I am giving you 1 minute time for this one again. So please think, analyze, and then answer. Hmm. So I have already received one response. Let's see about others. Another response I have received. Okay, let us see. So yes, Vidisha is correct because this is the generally for flow in the as I have said that for flow along a flat surface, consider it as a laminar flow. So we have Reynolds number is 5x by this one is our formula, right? So again, this Reynolds number can be written as u x by nu. From where this comes from, this comes from this one, where mu by rho is nu is that kinematic viscosity. Okay, so here I can write 5x in place of Reynolds number. I can write ux by nu. So see, in a general condition, as nothing is given, so I can consider only x as the variable because u for a certain case is same and viscosity is also same. So that's why this thing can be written like this way. So which is also root x, that is x to the power 0.5. So there should be the correct option. So good, Vidisha. So I hope that you understand this. So I am moving to this next question. I hope it is clear to you all. Okay, I am moving to this next question. So that is another concept is just try to if you I think that in the classes in the lecture note you have gone through this thing. This is a direct question based on this fundamental. So I am giving you 1 minute time to recall, else I will help you to solve this one. So if someone asks you this question, what is the importance of this boundary layer? So say boundary layer is like a resistance. So say this is a plate, right? If the flow is flowing, so it should flow freely. But because as it is flowing over this plate, the fluid particle experience some resistance and its velocity decreases. Because of this decrease in this velocity, a layer is forming, and this layer is known as a boundary layer. This layer is known as this boundary layer. So that is the fundamental of this boundary layer thickness. So I have received one answer. Let us see about others. What others are responding. Okay. Okay, I am giving you this idea about this concept. So, Pragya answered. Pragya answered option A. Yes, Pragya, your answer is correct. So now I am solving this for others. So say this displacement thickness. So boundary layer thickness generally represented by delta, and this displacement thickness is represented by delta star, which is displacement thickness. Okay. So what it helps? So it helps to measure the effect of boundary layer. So remember this thing, measures the effect of boundary layer on the outer inviscid flow. So that is the fundamental of this displacement thickness. So as I have said that if this is the boundary layer and outside this is the inviscid region, and this is our viscous region. So that displacement thickness measures what is the effect of this boundary layer on this viscid flow. Whether if the heat, say the surface is heating, I am talking about heating this surface. So how much heat this surface is in this viscous region is initially taking, and after this what amount is going to this region, that thing is measured using this displacement thickness concept. Okay, so inside this viscous region or this boundary layer region, what will happen? The velocity is quite less compared to the stream velocity. That means the velocity experience in this in viscid region is say u max. But in this boundary layer region, the that velocity is quite less and it is gradually increasing upward. So that is also another point. So this outer flow behaves. So that means what exactly this indicates? This indicates that the outer flow behave as if the walls are slightly displaced outward. So this outside fluid, what this outside fluid will see, the outer fluid will see that this is a wall, this is a bulgy wall. Like initially the wall is like that one, but this fluid will see this boundary layer as an wall. It's a resistance layer, we can say. So what is the formula? Just also remember this formula. That thing is also required. This is 1 minus u by u infinity into dy. So this u, so what is u and u? U means this velocity at a certain position in the boundary layer thickness region, and u infinity is the free stream velocity. Here, this is the u infinity in the. So the integration should be from 0 to 0 means this position, and infinity means here infinity refers to this inviscid region. So say up 5 mm apart from this surface, that will be 5 here. So in that way you need to find out this displacement thickness. So please remember this thing. So it basically this will help to study the effect of boundary layer on the outer flow. Outer potential is displaced due to this boundary. That is the option A is the correct answer. No, option B is not the correct because it is not the actual thickness of the boundary layer. Actual thickness is delta. The thickness where this boundary reaches 90, no, it is not. It is also not the correct answer. So the correct answer is option A. Okay. So I am moving to this next question. So this is the velocity profile in a laminar boundary layer over a stationary flat plate can be approximated what type of profile it is. So that thing already I have discussed. Anyone? So others please try to respond. So so anyone? Yes. So three people will say parabolic is the correct answer. So let us solve this one. So how these velocity profiles look like? So see this, if I talk about this velocity profile, this generally the profile that has been created after some derivation, that derivation is not required for your exam point of view, minus y by delta whole square. This is y by delta whole square. Okay. So basically, for this laminar boundary condition, as it is talking about this laminar boundary layer, so what will happen initially, the velocity at near the wall is zero, and it will move to u infinity at a certain level. So, and this thing, so that is our boundary layer, like this way, right? So here this delta is this one, and y means this one. Okay, so that is the formula. So this y will vary. Say if I have to take this point, if u is here, what is u? U means the velocity at a certain point. If the u is here, if the u you are talking about is here, then y is up to this. If the u is here, then y is up to this. So depending upon the point where y is u is situated, you have to take the value of y. And that is the formula for this variation of u and u infinity. So u infinity you will know, and the distance, boundary layer thickness they will provide and say that at a distance of 2 mm, so y is 2 mm, so you are asked to find u. So you just have to put this formula, which is y by w square. So that is the formula. So see, if u is u directly proportional to y square, so which is a parabolic profile. So the correct option is a parabolic profile. So I am moving to this next question. So the next question is in a boundary layer, the term that is generally neglected due to its small contribution in comparison to other is convective acceleration term, viscous term in the flow direction, pressure gradient term, or viscous term in the normal direction. So also that thing you have, I think that if you observe the previous assumption of this Navier-Stokes equation, you will be easily able to answer this one. Just let me recall you this one thing. So as the convective acceleration term, this viscous term, pressure gradient term, and all this term you remember in this Navier-Stokes equation, yes or no? So if you remember this thing, then you can easily answer this one. So please try and give me 1 minute time. Okay, I'm giving you this equation for your understanding. So Navier-Stokes equation I am writing for your better understanding. So the Navier-Stokes equation is, so this is the Navier-Stokes equation. Okay, you remember this term. So in this is the pressure gradient term. This is the viscous term. This is the convective acceleration term. So these three terms they're talking about. So which one should be negligible? Anyone? Am I audible? Okay, so this Navier-Stokes equation, as you have gone through this Navier-Stokes equation, so I hope that now you will be able to answer this. So this term is the convective term, this is the pressure gradient term, this is the viscous term, right? So from this assumption of this Navier-Stokes equation for this boundary layer approximation, so you can easily write this. You can say that there are three assumptions for this Navier-Stokes boundary layer assumption in this Navier-Stokes equation. The first is that the boundary layer thickness assumption. What are those assumptions? First is boundary layer is should be thin, right? So next is anyone? I think that someone has answered. Yes. So Pragya has answered option C. Let us see. So the next one is that the velocity gradient term du dy in the y direction should be quite greater than du dx, right? That means this one should be negligible. The third is dp dx should be small, or even it can be negligible. But the term is that which of these terms should be say either this term should be negligible or this term should be negligible. So there is two option there should be negligible. So in which option these terms come? So this gradient term comes here also, here, and these pressure terms come here. So all these three option looks to be the answer, right? Then how will you choose which one will be the correct option? So in terms of this boundary layer, which one is important? The viscous term is important, right? So in this viscous term, as I have said that in the x direction, this velocity gradient term is less. So the viscous term here should be less. That should be one answer. So this viscous term that will not be the answer because as this gradient term is small in the x direction, but the gradient term is more in the y direction. So in the normal direction, the viscous term will be more. So option D is not the correct option. So we can easily remove option D. Now the pressure gradient term. So this pressure gradient term should be small only in the x direction, but in the y direction there should be pressure gradient, as I have told that if this is the boundary layer, there should be sufficient pressure gradient among this y direction. Here nothing is mentioned about this pressure gradient, whether it is in x direction or y direction. So that will not be the correct option here, right? That's why I am cancelling this one. The convective acceleration term here, say though this term is less, but this du, that means the velocity gradient is less, but it should be multiplied with u right? They use the velocity at a certain point. So that's why this term should not be zero. Because though it is less, but if it is multiplied with rho and u, its overall product should be sufficiently high. So we can't neglect this term. As du dx in the x direction it is zero, so its corresponding viscous term should be negligible. So option B is the correct answer. So Pragya, I hope that you understand why option C is not the correct answer. So see, if other options like in the viscous term and all these terms are not given, so in the flow direction or in the normal direction, these are not given, then in that cases your answer will be correct. But here it is clearly mentioned that in the flow direction. Okay. So if in the flow direction, so the boundary layer condition is only because the viscous term we are considering along the y direction only. We are not considering along the x direction. That's why this boundary layer is forming. If the viscous term is along the x direction, then this velocity will steadily grows on decreasing along the x direction, but it is not happening. It is having same velocity along the horizontal direction, but it is increasing from wall to the top along y direction. Okay, so that's why this is our correct option. So I am moving to this next question. So it is another simple question. So I am just giving you 30 seconds to answer this one. In boundary layer theory, no slip condition at the wall implies what? Just please try to answer. Already I have got an answer. Others is a simple question. Please try to answer. Yes, this is answer option B. Yes, this option B is the correct answer because no slip condition implies whatever if it is a flat plate and the velocity of the particle, say this is a flat plate and this flat plate is moving at a velocity say 2 meter per second. That implies the particle near the wall also should move with 2 meter per second. Or if the plate, this plate is at rest, that means in stationary condition, then this particle should be at rest. That means the velocity at the wall relative to the plate should be zero. So option B is the correct. This velocity at the wall means the relative velocity. Okay. So relative velocity means if it is 2 meter per second, it is the velocity with which the plate is moving. And also the fluid should be moved with 2 meter per second. That means both there is no such velocity difference. So I can write u relative should be 0. Here also u relative should be 0. So some students just confuse among these things. Velocity at the wall is 0. So if the plate is moving at 5 meter per second, either the velocity at the wall should be 0, velocity of the particle near the wall should be 0. No. So this velocity of the particle near the wall should be 5 meter per second. The main motto is that the main motto here is that the relative velocity should be 0. So option B is the correct answer. So I am moving to the next one. Next question. So it's a numerical question. In case of flow through a circular pipe having radius r, what is the distance from the boundary layer? The value of the wall shear stress is 3 times the turbulent shear. So please try to answer. So I am just giving you this formula. Shear stress due to turbulence is equal to shear. So basically, if this is a flow through a circular pipe, here R is the radius, right? So at any point, say this is the any point, this is Y. So you are asked to find at this Y point what is the distance of this Y point where what is the value of the shear stress is 3 times the turbulent shear. Wall shear stress is 3 times the. So that is the question given here. Please solve and tell what will be the value of Y. That is the formula where tau T is the turbulent shear stress and tau wall is the wall shear stress. So I'm giving you 1 minute time. So please try to answer. Yes, option D. Yes. Pragya has answered option D. Yes, yes. So just remember this formula. This is the. So in the question, what is given? Given shear stress at the wall is 3 times that of T. So from this formula, I can write tau T is 3, 1 minus Y by R, right? So these two will be cancelled out. So I can write 1 by 3 is 1 minus Y by R, or Y by R is 1 minus 1 by 3, which is 2 by 3. Therefore Y is 2R by 3. So the correct answer is option D. Good, Pragya. So I hope that you understand this thing. So I am moving to this next question. It's a simple question, this one. Just a minute. So here the thickness of the boundary layer on a flat plate at a point P is given, and point Q, which is 1 meter downstream of A, is 3 centimeter. What is the distance of Q from the leading edge of the plate? So you just here use this formula of delta for linear boundary condition. So accordingly you will be easily able to solve this one. Okay, so please try to solve this one. Just I'm recalling you this formula. So this was our initial formula. From this initial formula, what I will got. So you just remember this thing. I'm not writing this thing. Please try to solve. I'm giving you 2 minutes time for this one. Please try to solve this one. Okay, I'm helping you with some hint so that you will be able to solve this one. So what is given in this question? Just see. The thickness of the boundary at a point P is here. That means this delta P is given as 2 centimeter. And what is given? Delta Q, which is 1 meter downstream of A, is this is your 3 centimeter. So this is at XP, at point XP, right? And this is at point XQ, which is 1 meter downstream. That means it should be this one plus 1, and it should be in meters as it is given, right? So you are asked to find the distance q from the leading edge of the blade. That means you are asked to find xq. Now, anyone? Also see, so as I have said that this is for a plate, for a single plate, what I have known that this Reynolds number x is ux by nu. So for a single plate, I can write Reynolds number x proportional to x. So therefore, I can write this one is root x. So that is the formula. So use this formula here. The p by xp by x cube. So now I think that you will be easily able to solve this one. Please solve and tell which one will be the answer. So anyone? So please try. Vidisha answered option B, 0.80. Uh, just a minute, just see the distance of the point Q from the leading edge. So that is already given, which is 1 meter downstream of A, right? So who is the partially correct? So Vedishi, you are partially correct. Not so you just find this XP, not XQ. So in the question, it is asked to find. Yes, yes, Vedishi, now it's correct. Yes, so that will be the answer. So that will be it's a 2 by 3. I can write 2 by 3 is XP. I can make it square XP plus 1, which is 4 by 9 is XP plus 9 XP 4 XP plus 4, or XP is 4 by 5, which is zero point 0.8. So therefore it should be 1.8 meter. So option D will be the correct answer. So in the exam also, if you are appearing for this NPTEL exam, please remember sometimes the question is quite easy, but we just confuse among this option, and to complete this question in a hurry, we just make mistake. So try to be patient while answering this question. Understand what has been asked in the question, and after that you please go through this. Okay. I'm moving to this next question. It's another theoretical numerical question. So it is also the same like this one, but here the concept is a little bit different from the previous one. So please try to answer this one. Again, I am giving you 2 minutes time for this one. So what is given? An incompressible fluid flow over a flat plate with zero pressure gradient. So that means it is talking about this talking about this boundary condition. The boundary layer thickness is 1 mm at a location where this Reynolds number is 1000. So Reynolds number and boundary thickness is given. If the velocity of the fluid along decrease by a factor 2, then the boundary layer thickness at the same location is what? So it's a tricky question. So just try. I'm giving you 1 more minute. So I'm giving you an hint. It's the same concept like the previous one. What we know that this is 5x by root rex, right? In this question, the velocity is given. So I know this Reynolds number is ux by nu. So the velocity of the fluid is that is streamline velocity is increasing. The boundary thickness at the same location. That means x is constant. So from here I can write as the x is constant, same location. That means x is constant. I can write this one is proportional to Reynolds number. Again, at the x is constant and this one should be constant. So only u is variable. So that means here this is proportional to 1 by u, right? So now you can solve this one. So use this one to solve this thing. So Berisha's answer option B. Yes, yes, it's the correct answer. So that's why I say it's a simple thing. This one, this should be equal to root u2 by u1. In the question, it is given what is u2? u2 is 2 times u1. It is increased by 2 factor. So we are asked to boundary layer. We are asked to find lambda delta 2. So delta 2 is sigma 1 by root 2. Sigma 1 is given as 1 mm. So 1 by root 2, which is 0.71 mm. So the correct option is option D. Can you understand this? So I am moving to this next one. Okay. So this is an important question where just I am first explaining the question and we'll tell you how to solve this one. So in this question, this water velocity of the water is given at a certain temperature, right? So the boundary layer thickness at the end of the plate is you need to find out. Density and viscosity of the water are given. So the thing is that so as you have to find out this boundary layer thickness, you do not know which boundary layer formula you need to ask because either it's a laminar flow or turbulent flow. Mostly say as the velocity is given, velocity no, as the velocity is given. So you first have to check the Reynolds number, either it's laminar or turbulent. Okay. So if the Reynolds number remains less than 5 into 10 to the power 5, then it's a laminar here in this case. So just check. For a laminar boundary layer, not laminar flow, I am talking about this laminar boundary layer. For laminar boundary layer, the Reynolds number should be less than 5 into 10 to the power. This one should be the value. So first, please try to find out this Reynolds number. Now, Reynolds number, please try to find out because already it is given. You know this formula of Reynolds number. U x by nu. Nu is mu by rho. So calculate the Reynolds number. And if the Reynolds number is less than this, then you have to use this formula. Else you need to use other formula. Check. So I'm giving you 1 minute time, 2 minute time to solve this one. So first calculate this Reynolds number. Any answer? So I'm just calculating this Reynolds number for you, which is u x by nu. So first I calculate nu. Nu is mu by rho. Mu is given here. And mu is 998. So if you calculate, it will come around the same value, 1.00 into 10 to the power minus 6. So this u is 1.3, x is 20 centimeter, which is 0.2, and this one is 1.004 into 10 to the power minus 6. So that means it is approximately 2.6 into 10 to the power 5. So Reynolds number, this is, so the Reynolds number is less than this one, so we can easily use this formula. So now just use this formula and just tell me which one will be the answer. Just giving you 1 more minute. Yes, Rishi, you were right. Big B, you were also right. So option C is the correct answer. Okay. So that means 5 into 0.2, and this one is 2.6 into 10 to the power 5. Accordingly, we will get the answer we will get is 0.0019 meter, which is around 1.9 mm. So the correct answer is option C. So it's a tricky, this types of tricky question may come in exam. So please go through certain types of question. The fundamental concept is same. First you need to find out the Reynolds number to check whether it's come under the laminar boundary condition, not laminar flow. Remember this thing, laminar boundary condition. If it comes under this laminar boundary condition, then you have to apply this boundary layer thickness condition for this laminar boundary flow. Okay. So this is our last question. This is based on the fundamental till now what we have learned in this live interacting session. So please try to answer this one. This one is the last for today's live interacting session. So use your concept, analyze and answer. So the low Reynolds number indicate what? So just remember this low Reynolds number. Reynolds number means what? Reynolds number means inertial force by viscous force. So if the Reynolds number is low, that means, so just check. Yes, good. Yes, Vidisha, you are correct. Yes. So see, as the low Reynolds number means in a low Reynolds number means inertial force by viscous force. So low Reynolds number means the force should be more. So we know that if the viscosity is more, thick boundary layer should be there, and so it is option C. So P is corresponds to option 3. Now coming to Q, Q means inertia force should, high Reynolds number, which is equivalent to inertia, more inertial force and less viscous force. So that means thin boundary layer. So option 2. And adverse pressure gradients means positive pressure gradient, more pressure gradient. So we know that if the del P by del, we know that if del P by del X greater than 0, so flow separation will be there. So in case of adverse, flow separation should be early. And favorable boundary condition means del P by del X less than 0. That means the less chances of boundary layer separation, or the flow can easily stick with the boundary. So that's it's in option 4. So option A is the correct answer. So good that Disha, you have answered it correctly. So option A is the correct answer. Up to this, any confusion for today's class? Any confusion? So if we do not have any confusion, so we'll wind up today's class. So please let me know if you have any confusion. So also remember one thing, whatever I have taught in this today's classes, please go through these classes and earlier notes. And this has been uploaded through the link that has been provided from the NPTEL side along with the feedback form. So if you go through this link, you will find this recorded video and also this lecture notes. So hope that you will find this for your exam. And if you go through this concept and you are not able to understand any concept, you can mail me, or you can also put down the question in my YouTube where this video has been uploaded. Okay. So I hope that you understand these classes and thanks for joining and have a good day.